Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. So we meet again in this online meeting, and this time is asynchronous because I couldn't teach the class this morning. So I apologize, and therefore I would like to present this as an asynchronous discussion for our class today. So previously we have discussed about parallel transport, right? And also how parallel transport can be related to the geodesic equation, okay? And so from that we can try to define curvature, right? We came to the conclusion to the definition of curvature, that is the failure of a vector to remain parallel with respect to its original direction when transported along a closed loop. Okay, so in my previous example, if I have a surface of a sphere, okay, we know intuitively that surface of a sphere is curved. Now I can draw any arbitrary loop or closed loop, yeah, or contour. For example, I'll take the loop to be 1, 2, 3, back to 1. Okay, this is my arbitrary contour. Now, I can transport any arbitrary vector, and in this case, the vector is a tangent vector. Let's say that this is the vector. I start at point 1. Yeah, this is a tangent vector. I want to transport this tangent vector along this closed loop. So I want to start from 1, and eventually I want to go back to position 1 again. Okay. Now, I can do it. I can pick any path, yeah. But if I want to go from 1 to 2, so as it goes along the equator, then at 2 the vector stays like this. But then as I bring 2 to 1 to 3, you can imagine that the vector now becomes is still tangent to 3, but it goes like that. And when I bring the vector from 3 to 1, you can convince yourself now that the vector now has taken this direction. So now the vector, when I bring it, when I transport it parallel along, when I do the parallel transport along a closed loop on this manifold, the vector fails to be parallel, to remain parallel. So this shows that the manifold is curved. So here I'm trying to show the application, or the what it means to be a curvature. Okay, so yeah, we defined that previously. So this is the formal definition of curvature. But if we only use this as a tool to prove or to attack whether any manifold, any arbitrary manifold is curved or not, we will face a trouble. We will be having problem. What is the problem? You see here that if you draw any arbitrary closed loop, it might be that with the choice of your closed loop, the vector can be parallel when it is transported along its the closed loop. When that happens, that's not necessarily the proof that the manifold is flat. Okay, because I can for example pick the closed loop in this case, in this example of a sphere, to be along the equator. Okay, this is the great circle or the equator. This is a closed loop. If I bring the vector to parallel transport along this equator, it will come to the uh, point one, to the same point, undisturbed or still remains parallel. Why? Well, we know that because parallel transport, from the parallel transport, that geodesic is the curve which is the straightest, which this is the curve when you transport your vector along that curve, then the vector is the most parallel one. Okay, so if you transport along the geodesic, obviously the vector is still parallel, but it doesn't prove that that the manifold is flat. No, because you transport it along the equator. If you pick another curve other than the equator, you can show that the vector is not parallel. So in that sense, proving a curved space or a curved manifold is easier than proving that the manifold is flat. Why? Because when you want to prove that the manifold is curved, you just need one example, or you just need one example, one closed loop where the parallel transport fails to become parallel. If you can find such a loop, only one loop, then you can say that the manifold is curved. But if you want to say that the manifold is flat, you have to prove that all possible closed loops, all possible closed loops that you can imagine, that you can draw on this manifold, give you a parallel transport, and that is harder to prove, right? You have to uh, check all. Maybe there are infinite possibilities of closed loops, right? And so in principle, you have to check them all, and you have to make sure that all possible closed loops give you parallel transport. If only one closed loop fails to give you parallel transport, then your manifold is not flat. So in that sense, proving the manifold is curved is easier than proving the manifold is flat. But even so, this kind of definition is not really practical for us to check or to investigate the flatness or the curvature of a manifold. We need a more qualitative tools, so that when you can calculate that, we can be sure that the manifold is okay. The manifold is flat, or the manifold is a curve. Okay. Now, can we devise such a thing? Well, fortunately, we can. So that's the case that we want to discuss today. All right. So imagine that I have 2 points in space. Yeah. On a manifold, point one and point two. Okay. Now I want to connect point one and two with a closed loop. I can obviously imagine any arbitrary closed loop that pass through one and two, right? But let me just draw it like this. I want to do it like this. Okay, so here's in that sense, I can go from one to two by choosing these two paths. Let's call it let's call this point like 3, sorry, this is point 3, this is point 4. So the first choice, I'm going from 1, 3, 2. Okay, so I arrive at 2. Another choice is that I'm going from 1 to 4 and to 2. Okay, all right. So in this sense, both describe a closed loop. But now here's the case. When we know that the parallel transport, as we see here, parallel transport amount to doing the what do you call this? The covariant derivative of the vector. Okay, so saying that I'm doing parallel transport from 1 to 3, and then from 3 to 2 is amount to saying that I'm doing a parallel transport along. Let's say that this is the covariant derivative is given by nu, while this one is different covariant derivative is mu. Okay. Now, if I choose the second choice, this is the same as 1, 4 is the same as 3, 2. So this is del mu, and 4, 2 is the same as 1, 3, and this is del nu. Okay. So what do I do? Actually, what I want to do is actually I want to work this double covariant derivative on our vector. So basically, I want to calculate like this. The question I'm asking is del mu works on del nu that works on V alpha is the same as del nu that works on del mu that works on V alpha. Okay, that's the question. Is this the same? Right? If this is the same, then it describes that the choice of path is commutative. So it doesn't matter where you go from 1 to 2. It doesn't matter which way you pick when you go to from 1 to 2. Your vector will still be parallel if this is the same, if this is an equation. Okay, if not, then the state of your vector at 2 will depend on the choice of path you make, right? And that's what we want to prove. So asking this is essentially asking the commutator of partial of the covariant derivative, and then you work it on a vector. Okay, so this is what we want to calculate, and we want to calculate whether this is 0 or not. So this is saying like this, minus. Okay. Now what do we do with this? Well, we can just work it on. We know how the covariant derivative work, right? So we can just work it out. Well, first of all, I would like to work the covariant derivative. So we know that the covariant derivative gives you a tensor. So basically, this is a tensor. This is a tensor rank 2, right? This is a rank 2 tensor. This is a rank 2 tensor. So you apply the covariant derivative of del mu to a covariant tensor, and here you apply the covariant derivative of del nu to another rank 2 tensor. Okay. Okay, let's work it out first. Let's work this one first. So this basically is just partial mu of, let's keep the one in the parentheses as it is first. Okay. Now it is a rank 2, so it has two indices. So we need to have two terms for the for the gamma functions, or the, what do you call this one? Christoffel, for the Christoffel symbol. Okay, for the Christoffel symbol, we have, let's take the new index first. So this is mu new, this is lambda, lambda v alpha. Okay, now let's take let's work on the alpha index. So this is alpha mu lambda del nu v lambda. Okay, so minus the second term. So the second term will be put like this as well. This is the partial nu del mu. Sorry, this is del mu v of alpha minus mu nu lambda del lambda v alpha. Sorry, this is the other way. Yeah. Well, it doesn't matter because Christoffel symbol is symmetric, but I'm just wanna make it consistent. And this is nu lambda alpha del mu v lambda. Okay, so here is like this. Well, we know that precisely because the Christoffel symbol is symmetric, so gamma lambda mu nu is the same as gamma lambda nu mu. Okay, so this is the same, this is the same, so we have a cancellation for the second term on each term. It cancels with that, right? Because this is minus, so it becomes plus. Okay, anything we can cancel? Well, not yet, but we can express it in more explicit way. So this is partial mu of what? Partial mu of, this is partial nu of v alpha plus gamma alpha nu. I'm going to use the same lambda, v lambda, like this. Okay. This is for that one, okay? Plus, this is gamma mu lambda alpha. Now we open this one as well. Partial nu v lambda plus gamma. Well, this one should be lambda because this is lambda, right? Now this is new, and I need another index. I'm gonna call it sigma to label v, the sigma. Okay, it's minus this one, minus partial nu of partial mu of v alpha plus, what is this? Gamma alpha mu lambda v lambda, yeah. This minus as well. Gamma alpha nu lambda. This is just partial mu v lambda plus gamma lambda mu sigma v sigma. Okay. Now we can see that this becomes partial mu working on v alpha. And this is commutative with partial mu working on v lambda. So I can cancel this. Okay. So what is left is just we have partial mu of gamma alpha nu lambda times v lambda plus I have gamma alpha mu lambda partial nu working on v lambda plus gamma alpha mu lambda gamma lambda nu sigma v sigma. Okay, minus partial nu working on gamma alpha mu lambda v lambda minus gamma alpha nu lambda partial mu v lambda minus gamma alpha nu lambda gamma lambda mu sigma v sigma. Okay. Well, we can still open this expression. So this one becomes partial mu gamma alpha nu lambda. So this like this, right? Plus gamma alpha nu lambda times partial mu of v lambda plus gamma alpha mu lambda times partial nu on v lambda plus gamma alpha mu lambda gamma lambda nu sigma v sigma minus partial nu of gamma alpha mu lambda times v lambda minus gamma alpha mu lambda times partial nu working on v lambda minus gamma alpha nu lambda partial mu v lambda minus gamma alpha nu lambda gamma lambda mu sigma v sigma. See, can we have anything we can cancel? I think yes, we can, yeah. You see here we have gamma alpha nu lambda times partial mu v lambda. This is precisely that one, yeah. Okay, we can cancel this. And also we can cancel that. Yeah, this is precisely that one. Okay, so it reduces our equation into only this one. I'm joining the first two, these first two, yeah. Alpha mu lambda v lambda and plus that one gamma alpha mu lambda gamma lambda nu sigma v sigma minus gamma alpha nu lambda gamma lambda mu sigma v sigma. Okay, so this is basically the left hand side is just like this, right? Okay, so this is left hand side and this is the right hand side. Now I can change the right hand side so that all of them has v of lambda. Can we do that? Yes, we can. So now I can just write down like this. Okay, I pull the v lambda out. But for these two, we have v sigma instead of v lambda. What can we do? Well, we can rename sigma as lambda and lambda as sigma. So by doing that, I'm having sigma nu lambda, right? And this one is alpha nu sigma mu lambda. So now all of them is multiplied by v of lambda. Or I can simplify them into this expression alpha lambda mu and nu. This is v lambda. Okay, so the question whether the path is commutative or not is amount to asking the question whether this object, the R with 4 indices, vanishes or not. Okay, now we have to check what this is first. See, the left hand side is all a tensor. Okay, the left hand side is like this. This is a tensor. This is a tensor. This is tensor rank 3. This is tensor of rank 3 as well. And since the left hand side is tensor, the right hand side is also, it also must also be a tensor. Okay, since V lambda is a tensor or rank 1 tensor, then this one must be a rank 4 tensor. Okay, so this one is a rank 4 tensor because it has 4 indices. Okay, it has 4 indices, and this tensor is known in the literature as, I'm going to write down, this is the alpha nu lambda comma mu, yeah, minus alpha mu lambda comma nu plus alpha mu, I'm using sigma, yeah, here sigma, sorry, this is nu lambda, okay, minus alpha nu sigma mu lambda. Okay, this is the rank 4 tensor that we define. Okay, and this in the literature is known as Riemann curvature tensor. Okay, so this is called the Riemann curvature tensor. Now, we name it curvature tensor not without no reason. Okay, because this tensor is the tensor that characterizes whether a manifold is curved or not. Okay, if a manifold is curved, then this Riemann curvature tensor must not be 0. At least one of its component cannot be 0. If a manifold is flat, then its Riemann curvature tensor must be 0 identically. So all components of Riemann curvature tensor must be 0 if the manifold is flat. So now we can characterize the curvature of the manifold by calculating the Riemann curvature tensor. Okay, so yeah, I think this is the one that is going to be important in our discussion on gravitation, yeah, because this is the one that we are going to use when we want to characterize space-time, whether space-time is curved or not. Well, this is a tensor with 4 indices. In 4 dimensions, it means we have 4 to the 4. 4 to the 4th components. We have 4 to the 4th components, yeah. So you can imagine 64 times 4, right? So there are lots of components to calculate. Okay. Well, fortunately, we don't have to always deal with the Riemann curvature tensor. Riemann curvature tensor can be what we call we can contract it. Yeah, I can contract it from a rank 4 tensor into a rank 2 tensor. I call it R mu nu. And R mu nu is defined as the contraction of Riemann curvature tensor, the contraction of the first and the third index of Riemann curvature tensor. So the first and the third. Okay, so this is the definition. Okay, now R mu nu, if you contract it, if you work it out, our mu nu can be given by this. Mu nu, this is alpha comma alpha minus alpha mu alpha comma nu plus gamma mu nu alpha gamma sigma alpha sigma minus gamma alpha mu sigma gamma sigma alpha nu. Okay, so this is the component of the rank 2 tensor that we just created. And this rank 2 tensor bears a name. This is what we call the Ricci tensor. Okay, this is the Ricci tensor. Okay, well, I think I'm just gonna stop it here. We'll continue on Monday, inshallah. Yeah, hopefully we can meet on Monday. Okay, thank you very much. See you on Monday. Yeah. Assalamualaikum warahmatullahi wabarakatuh.